Take a look at these diagrams. So as you can see, these diagrams are about projectile motion on an inclined plane. So this is your inclined plane, and this is another incline, and so on. What I want you to notice here is the path of the particle. So what do you mean by this? So this path, which is also called trajectory. So the trajectory of the particle when it is projected from an inclined plane. Take a look at this second trajectory. This definitely feels like wrong, right? Take a look at this third trajectory. It goes good, but here you see here is the problem. So what is happening? Why are a lot of people confused about the trajectory of a particle projected on an inclined plane? Well, the reason for this is when you have a projectile which is projected from a point on a horizontal plane, this kind of diagram you will see, and the trajectory is said to be parabolic, right? So this is parabolic, and you can also see that this point here where the particle attains the maximum height, and you draw a straight line, vertical straight line from here. This will be the axis of the parabola. And the trajectory is completely symmetric about this line. So this side, you can feel that this is symmetric. And what happens when you go to an inclined plane? When you go to an inclined plane and you project a particle from here, so what happens? Somehow, because of this incline, the plane getting inclined, people start to feel like that the path, this parabolic path, the path will still be parabolic or maybe not. But it's very easy. We will see the mathematics also involved here. The path feels still like parabolic, but what happens that people have a tendency to tilt the axis of the parabola also, and draw a line which is symmetric, a line of symmetry, which is like this. This is the axis of parabola, as you can see. Now you begin to see it. It's like from the inclined plane, it's like this is the ground, and this is the point of maximum height from the inclined plane. If you measure height like this, and you get the axis of parabola like this. But my question is that, is it right? Because in the first diagram, as you can see, you can feel that the axis of parabola is tilted. It's like this. Yeah, and in the second diagram, you can feel the confusion. This is definitely wrong. This is the trajectory is not going to be like this, because the particle is not going to come back like what is happening here, and the particle is not going to go into a straight line, which is happening in the third diagram. So this is definitely wrong. What I want to explore is that on an incline, the path of the projectile, how would it be? So what will be the path of the projectile if it is projected on an inclined plane? So this is option, let's say, 1, and the other idea you can think is like the particle still goes like this, and the axis of parabola is still vertical. So which diagram, 1 or 2, as you can see, this one or this one, which one is correct? Because intuitively you might feel like both of them can be true. We need to use some mathematics to figure out. But let's deepen our understanding, deepen our intuition, and without going into mathematics, let's reason. First of all, I would like to show you something, some of these figures. Like, let's see here. So whoever made this, so now you see from P, the particle is being projected from P to Q. As you can see, the arrow is here, it's going like this. So when the ground beneath the particle from where it is projected becomes horizontal, then the intuition of this person is to take a parabola with vertical axis, not a tilted axis, right? So, and this also looks like, right, because why would you tilt your parabola in this situation? How about this? Take a look at this this questions about like horizontal projection. So this is like this is, you can say that this is your ground, and from some height above the ground a particle is projected horizontally. And in that case also, I see mostly people are doing the right thing, and they are making a parabola with a vertical axis, and the axis of this parabola, this is your parabolic trajectory, and the axis is right here. So there is a good amount of evidence that the axis of parabola will always be vertical. Do you feel it? But these kind of evidences doesn't matter. We need to pin out the mathematics behind it. Or we can also be a little bit more sure with this intuitive idea. Let's think about this. So suppose that this is a tower, and here is your ground, and this is an inclined plane kind of a structure, and both of them have same height. Let's say that this height is h, this height is also h. And what we are doing is like we're taking a particle and projecting it from the top of this building, from here, and then from the top of this inclined plane. And what's going to happen? Will it matter for this particle, like what was its past history, where was it kept? Because you are projecting it with an speed u, let's say, and some angle theta from the horizontal. So you have u cos theta speed here, and u sin theta speed upward. And similarly here, if this angle is theta, you have u cos theta speed here, and u sin theta speed upward. So this from where it is being projected does not have any impact on the trajectory of the particle, what kind of motion it's going to feel. Afterwards, it will have a downward acceleration g. Here also it will have a downward acceleration g. So all the parameters are same. Then why would one think that in this case it will be, the trajectory will be like a parabola with vertical axis, but in this case the parabola would get tilted? You see, there's no reason now to feel that the path will be a tilted parabola in case of an projection on an inclined plane. And maybe if you say like how are you sure that this is going to be a horizontal parabola in the first case, like here, why are you sure that the trajectory is going to be a parabola with vertical axis? I mean, if you are not, if you can't feel it, then let's just bring this big structure here, like, and imagine that this is a very big building, and you are projecting this particle on top of this building. Does it make sense now? Okay, so I think you might be getting an intuitive feeling about this. Another way I can tell you about this is like let's think about this parabola. The shape of the parabola, it's like there is an axis of a parabola, and the parabola is symmetric about its axis, and it goes like this. And what happens if you consider these points also far away from this is the vertex of the parabola. So far away from the vertex, the parabola tends to get parallel to its axis. I mean, take a look at this standard parabola y squared is equal to 4ax, and it's like this. And if you figure out the slope, so 2y dy by dx is equal to 4a, and dy by dx is going to be 4a by 2y, and from here you can say that y is root 4ax, and x is definitely positive in as you can see, this is your x-axis, so the x coordinate of the points are definitely going to be positive because it's the parabola is not going on this side. Anyway, so this is 2a by y, and for y I can put root 4ax, and if I say that limit x tends to infinity and think about the slope, so you see you will get a very big number down here, and this will tends to 0, right? So you can also say that the y is either this plus or minus because the height is up or down. In both the cases, like from here on this upward side, you can see that the slope is getting 0, and it's like 0 positive, and from here you can see that the slope is getting almost 0, but from the negative side slope is 0 negative, but the slope is getting limiting to this value 0, which means that the parabola is going to get eventually parallel to its axis. So if that is the case, then you can understand, like suppose this inclined plane is very long, and you have the path of the projectile, you project it like this, and you say that this is going to be, the axis of parabola is going to be tilted like this, and then it will be symmetric about this. So in this diagram it's okay, you can't see it coming back. In this diagram it's okay, but let's make this kind of a diagram in which the speed of projection is this is your inclined plane, and you project it with a very high speed, and it goes like this, and it hits its vertex, and then it starts to come back, and this is the axis, and even like finally you see that this will turn, and if this is your horizontal, this is your vertical direction, the path of the projectile is like this, and if it is a tilted parabola, it will cross this vertical line, which it can't, because now you see that from here the particle is coming back in the horizontal direction. But in the horizontal direction, if the speed is u cos theta, let's say this angle is theta and the speed of projection is u, this speed is going to be maintained throughout, and it can never get negative, so the particle can never come back in the horizontal direction, which it will if the shape of the projectile, if the shape of the trajectory of the projectile is a tilted parabola. Well, if that's not enough, let's go into the mathematics and think about this. I will first take the axis, this as origin, and I will like to take the axis along the incline, x axis here and y axis here, because if I take the axis as horizontal and vertical, you very simply see that the part of the trajectory, the part of the particle is going to be a parabola with vertical axis. But I would take axis like this along the incline and perpendicular to the incline, and then I will resolve it like this: u cos theta speed along the incline and u sin theta perpendicular to the incline. And also I will take the acceleration, which is actually downwards, but because we are taking axis x and y axis like this, I will have to take the component. So you see, this angle is alpha, we need this angle of inclination also to get a component of g. This angle is alpha, so this angle is 90 degree, right? So this angle is definitely going to be 90 minus alpha. This angle is between vertical and along the incline, so this angle will also be 90 degree minus alpha. So you can resolve g as g sin alpha and g cos alpha. Okay, that's fine. And then you can write these equations like this is your origin, right? So x coordinate of the particle after time t, it will follow ut plus half at square. So this is your u, and after time t you have ut plus half, and the acceleration along x-axis is g sine alpha, as you can see here. So half of that acceleration is time t square. Similarly, you can write the y coordinate of the particle, and that's like this. Okay, so what we are going to do now, we to figure out the trajectory, to figure out what curve will it follow. We need a relation between x and y. So for that, you can divide the x by sine, the first equation by sine alpha, and the second one by cos alpha, and add them. When you add them, this term cancels out and you get this expression, right? So there is a t still here, sitting down here, and then from here you can figure out what your t is. Also, you can do some minor adjustments here, like you see this cos alpha will get multiplied here, this sine alpha will get multiplied here, and it will become cos theta minus alpha, or alpha minus theta, it doesn't matter. And this sine alpha cos alpha term from down here will get cancelled, and you will get an expression for t in terms of x and y, and you can put this t in any one of these relations, x or y, and you can eliminate t, and you can get the trajectory. So let's do that, and you see that the equation of trajectory is too complicated. Well, how to deal with it? It's quite complicated, but we will not go into it. Like we will not. It's not required to like pin down every details of this equation. What you can see here is like in this equation, if you expand it, you will get an x term, and you will get a y term, you will get an x square term, you will get a y square term, and there will also be an xy term. You can feel it, take a look at it. There will definitely be an x term and a y term, an x square and y square and xy. So from here, I would like you to think about if you have this kind of x-axis and y-axis, and you're thinking about parabolas which have an axis parallel to y-axis. So the simplest one you can think of is like y is equal to minus kx squared, right? So this kind of an. So I hope my viewers have some idea about graphs. So now if you have this kind of a parabola, which is just like a downward parabola, it's just like minus kx squared, but what is happening here, it's like it's getting translated in two directions. So you can think like this curve get translated here, and it goes up, and maybe it goes down, it goes backward. So this is basically this parabola. You can see two transformations you will have to do. You'll have to translate it in this direction, left or right direction, and up and down direction, and in that with these transformations you can get this kind of parabola, right? So what kind of equation will these parabolas have? It's like you are doing a transformation along the x-axis, so your x will be transformed by some value and your y will also be transformed by some value, right? So it's like the general equation will be like this. A little bit of graphical transformation required here. You can also see it like this. Take a look at this. This is our equation, and when you translate along x or y axis by some value, the y coordinate will suffer with this kind of a transformation algebraically, and your x coordinate will suffer with this kind of a transformation algebraically. This is basically this c here, you can also take it back and say that this is minus c, but what is the sign of this parameter a and c doesn't matter here that much. But what do you see, like in this form, if you have a parabola with an axis parallel to y-axis, this is the axis with an axis parallel to y-axis, in its equation you are never going to encounter an xy term. But here, if you see, this is your y-axis, this is your x-axis, and if you say that the parabola is tilted like this and its axis is still parallel to the y-axis, this is your y-axis, if the axis is still parallel to the y-axis, then how come it has this xy term here? Okay, so in this coordinate system, when you write down the equation of the trajectory, you get an xy term, and because of that you can say that the trajectory of this particle is not like this. It's not a parabola which has an axis which is parallel to the y-axis. So the parabola is not going to be tilted for sure. Okay. Yeah, also you can think about this in this kind of trajectories, they start from origin, so they should also satisfy this thing that 0, 0 point should satisfy it. So from there you can also get a condition like this, but that's not important. I am just thinking about that whether there should be an xy term or not. But okay, so this idea, this blue trajectory, is definitely wrong. Okay, so now let's think like how do you prove that the trajectory is going to be a parabola with a vertical axis? So take a look at this equation. This is quite complicated. This is coming from these parametric x and y terms as we saw before. So what I'm going to do now is like apply transformation of axis. I could have very simply gone into a horizontal or vertical axis, but here I will show you through transformation of axis. So suppose your x coordinate is like this and y coordinate is like this, and there is a point here which has a coordinate which is at an angle A from x-axis, and r is the radial distance. So you can write in terms of polar coordinates, you can write the coordinates as r cos alpha, r sin alpha. But if you rotate your axis, your new x-axis is this, and you rotate by an angle alpha anti-clockwise these axes. Okay, so you're rotating the pair of axes anti-clockwise by an angle alpha. What happens is that the new coordinate of this point P would be like you can see, take a look at this angle is a minus alpha, and from here you can write the new coordinates as r cos a minus alpha, r sin a minus alpha. So let's denote the new coordinate by capital X and capital Y. So you see, you expand these terms and you will get this thing. So cos a minus alpha is cos a cos b plus sin a sin b, and sin a minus alpha is sin a cos alpha, sin a cos alpha is here. So deliberately I have written this first term here, and sin b, which is sin alpha, and minus cos a is here, right? So expanded this, and you can say that these terms here, r cos alpha was your previous x and this is your y, so previous coordinates in the previous system, so you can replace them by x and y. So what you get is you can say that the new x and new y coordinates are like this. You can also represent it using a matrix notation, and this is the very famous rotation matrix which we have here. Well, so what now? So what we are going to do is like we are going to take correct our axis. It's not correcting, we are taking a new axis for simpler calculation, and this axis is now, x-axis is now horizontal and the y-axis is now the vertical. And then you see that what we have done, this angle is alpha, so this angle is alpha, so this angle is also alpha. So we are doing the same thing. We are rotating the axis by an angle alpha anti-clockwise. So what's going to happen now? So your new x coordinate would be your previous x coordinate times cos alpha, as you can see here, and previous y coordinate times sin alpha. Don't worry about it. You see, it's very interesting. This term and this term will cancel out, and you will get ut cos theta cos alpha plus ut sin theta sin alpha. Take ut common and you will get cos theta minus alpha term. That makes complete sense, because now you see that this is your u, this angle, this complete angle was theta, this angle is alpha. So if you think about this angle, this is theta minus alpha. So the projectile is always going horizontally with a speed u cos theta minus alpha. So in any time t, it will cover this much of distance. So it's in the new coordinate system, the x coordinate is going to be very simple. So interesting. And then the y coordinate, if you apply this transformation, you multiply with minus x sine alpha and plus y cos alpha. And what happens now? This time the ut term, does it get, none of the terms I think will get cancelled out. With the ut term, you will get cos theta sine alpha with a negative sign, and sine theta cos alpha. So this is basically sine theta minus alpha. You take ut common out, and the half gt square term will be sine square alpha, will be cos square alpha, which will become 1 if you take minus half gt square common, and you will get this. Whoa, so take a look at this. So we have come back to home, to the simpler horizontal and vertical axis, and the equation of motions are quite simple, as you would expect. Just like this angle of projection is now no more theta because it was from the incline, but here the angle of projection has become theta minus alpha, and the equations have simplified themselves. And in this coordinate system, if let's first put like theta minus alpha is equal to beta, and then write it simply x and y, and then you can take out t from here, from the first equation, and then put it in the second equation. You get a very simple equation of trajectory in the new coordinate axis, and this is definitely a what do you call it, downward parabola, as the students like to call it. You see, you have an x square term only, and you have an x term only, okay, no xy term. So in this axis, in this coordinate system, the parabola which you are looking at is definitely a downward parabola, because the coefficient of x square is negative, and the axis is going to be along the y-axis, right, because there is no xy term. And also, if you know like this, if y is equal to x square plus bx plus c, quadratics, if you know about this kind of quadratics, so if you plot them, you get if a is greater than 0, you get this kind of a parabola with an axis is parallel to the y-axis, and if a is negative, you get this kind of parabola where the axis is again parallel to the y-axis. So this time we are definitely getting this kind of a parabola, right? So that's very simple. So now the situation is resolved. The trajectory is just like this one, and the slope where does the slope, this is the point where the slope gets 0. The axis will be passing from here, and where, like, what is the equation of the axis? I want to think about the equation of the axis. How can we go about that? So dy by dx here is going to be 0. So first we calculate the dy by dx, and you can differentiate, and you can get this x term will vanish, and this x square term will become 2x. So you will get this kind of dy by dx, put it equal to 0, and what you get, x is equal to u square sine beta cos beta by g. Okay, and if you notice that this is if you multiply like 2 above and below, so you will get this u square sine 2 beta by 2g, and this is half of the range which we normally use. Like, range is, what is the range? I mean, the range depends on like till where does it go, but suppose that this was a flat land, so this would have been the range, and half of the range, so x coordinate, like here the x coordinate will be r by 2, so this is what we get here, r by 2. So the equation of the axis is this one. So that's it. So whether you are projecting a particle from an incline or from any other point on a horizontal plane, or from some tower or anything like that, so the path of the projectile on a surface close to Earth's surface will always be a parabola Okay, the parabola, but with vertical axis. Okay, so it's like suppose you have this kind of a situation. You are projecting a particle from here and it goes, let's say, to this building, and this is like a big building with a inclined slope. So you project it like this. It doesn't matter from where it is getting projected and where will it reach. During free fall, the trajectory will always be a part of a parabola which has a vertical axis, like this. Thank you.